Hi, grade 12s. We're on day 11, finding the x-intercepts of polynomial functions. This is the last lesson that we have in the polynomial functions unit. So if we are looking for the x-intercepts or the roots or the zeros, as we saw on our graphing calculators, of a polynomial function, so where it meets the x-axis, we can do one of two things. The first is to graph the function and read the x-intercepts off the graph, or get the graphing calculator to do it. Algebraically, which can often be more accurate, we can factor the function and let the individual factors equal 0. Let the individual factors equal 0. Sorry, I got interrupted. I could have repeated myself a few dozen times there. Okay, at the x-intercept, the sign of the function changes. I'll explain with a picture what I mean in a second. But the sign of the function changes if the x-intercept are of odd order. So, for instance, don't write this down. I'm just going to tuck it in here and erase it in a second. If I have a function that has this in it, I have an x-intercept of 3, and it is of order 3, which is an odd order. That means my function is going to go from positive across the x-axis, sorry, negative to positive across the x-axis at 3, or it's going to be in the positive side of things, going to the negative side of things at 3, because it's an odd order. So it cuts across the x-intercept or the x-axis at that x-intercept if it's of odd order. The sign of the function does not change if the x-intercepts are of even order. For example, don't write this one down. If you have within your polynomial function x minus 2 squared, that's of even order. That means you have an x-intercept of 2. But since it's of even order, that means the function won't change sign. So the function will be positive and continue to be positive, or that function will be negative and continue to be negative. It doesn't change sign. I like to think of it as a turning point or a bounce, whatever makes the most sense to you. For this example, for f at x equals 9x squared plus 24x plus 16, find the x-intercepts. So we can draw a picture of the graph and read it off the graph. I don't happen to have a graphing calculator handy, so I'm going to factor it. So this one does not have a greatest common factor other than 1, so I am going to have to decompose it. So I am going to split apart my 24x into 2 parts such that they add to 24 and multiply to whatever 9 times 16 is. So 144. So my two numbers nicely are 12 and 12, and everything is positive. So I'm going to decompose that 24x into 12x, 12x, 16, and now I can factor that by grouping. My first two terms, I see a common factor of 3x, which will leave me 3x plus 4 in brackets. For my second two terms, the 12x and the 16, I see a common factor of 4, and in the brackets 3x plus 4. All right, final answer. That common bracket of 3x plus 4, and coincidentally the leftovers are also 3x plus 4. Now that's a little ugly. Those two brackets show me what my x-intercepts are, but for those of us that just find that a little bit odd, how I can find my x-intercept is to set each one of them equal to 0. So for your x-intercepts, my y value is 0. So if I have two things being multiplied together to give me 0, that shows me my x-intercepts or my zeros. I'm going to solve as if one of the brackets were equal to 0 or the other bracket were equal to 0. They happen to be identical. So I'm going to subtract 4 from both sides and divide by 3, and I have an answer of x equals minus 4/3. That is my x-intercept. I'm going to write it as a point. Okay. I can rewrite my function, if you like, as 3x plus 4 squared. Recall from the last slide, at the x-intercept, which we know is minus 4/3 0, the sign of the function changes if the x-intercepts are of odd order. The sign of the function does not change if the x-intercepts are of even order. So in my most simplified form, my function is that, which is an x-intercept of minus 4/3 of even order. So that means my function will change sign about that x-intercept. So if I'm going to approximately graph this thing, I know that it has a y-intercept of 16, which is above my graph, so like way up here. And I know I have an x-intercept of minus 4/3, which is to the left 1 1/3 square, approximately right there. And I know at that x-intercept, my graph is going to change and the sign of the function is going to be positive, or in the upper half, both sides of that x-intercept. So my graph would be upwards and also upwards to the left. Well, we already knew that because I have a quadratic and with a positive leading coefficient, so I already knew that as I go to the right, my function is going to go upwards, and as I go to the left, my function is going to go upwards as well. So it just confirms for us at the x-intercept that I'm going to be staying positive and going upwards. For example 2, we have f at x equals 3x cubed minus 9x squared. So I'm going to find the x-intercepts again and find their order as well. So my function in factored form, I see a 3 and an x squared has a common factor. I would have an x, subtract 3 in brackets, and I have factored that using greatest common factor. And that is fully factored. So I have two x-intercepts. When this is equal to 0 and when that is equal to 0. So I have an x-intercept of 3. If I want that bracket set equal to 0 and I put a 3 in there, I would get 0. My other x-intercept is 0. This one has an invisible power of 1. So this is an odd order. That means at this x-intercept, which is odd order, my function will change sign. So it will be positive to negative or negative to positive. That means it's going to cross the x-axis at that point. For the other x-intercept, the 0, 0, 1, it has even order. So that means it's going to have the same sign on both sides of that x-intercept, which means it's going to turn around or bounce at that x-intercept. Okay, let's have a look at our graph. We know that we have an x-intercept at 0 and at 3. We know that at 3 it's an odd order, so the function is going to pass through it. And we know that this is a cubic that is an odd degree. Sorry, that is an odd degree. And it has a positive leading coefficient. So any odd degree, sorry, I can't do two things at once. There we go. Any odd degree function reminds me of the line. With a positive coefficient, it goes up to the right. So this is a cubic. It's going to do a little bit more like that. But I know my end behavior, and that helps me draw it. I know at the x-intercept of 3, it's going to change sign or pass through that x-intercept, and it's going to be going upwards. I know it has a turnaround or a bounce at the 0, so it is going to do that. And it follows the shape that I was expecting from the end behavior that I know. As x goes to the right, that function should increase upwards, and as you go to the left, negative, the function should go downwards. And that's what I expected to see. To verify what we mean by changing sign is I'm going to look to the left of the of the 0 x-intercept and just to the right of it and show you that it keeps the same sign. I've said that it's negative on both sides, so my function is negative here below the x-axis and negative here. Just to prove that that's true, let's substitute those values into the function. I have 3 minus 1 cubed minus 9 times minus 1 squared. Do exponents first. You'll get 3 times minus 1, which is negative 3. Take away 9 times minus 1 squared, which is positive 1. Take away 9, we get negative 12. So our function is negative, or below the x-axis, at minus 1, and it should also be negative to the right of that exponent. 3 to the 1 cubed minus 9 times 1 squared equals 3. Take away 9, which equals negative 6. So that is what we mean by it has the same sign on either side of that x-intercept. It turns around, but it stays below the x-axis. To the right of, and we'll look on either side of the 3, let's look at f at 1, which we already knew was negative, and f at 4, which is on the other side of the 3, and see what we get. Put a 4 into the equation. Is 3 times 4 cubed is 64 minus 9 times 16, 192 minus 144, which is 48. So my function going from 1 to 4 changes from being below the x-axis to above the x-axis. So it passes through that x-intercept 3 because it has odd degree. For our next example, we're going to look at 9x to the 4th minus 52x squared plus 64. So first thing we were asked to do is to find the x-intercepts, and that always helps us to graph it clearly. So I am going to factor this thing. It's a little ugly. So I am going to decompose this thing. I need two numbers that add to minus 52 and multiply to 9 times 64, which is 576. And it would take us a few minutes to get those numbers, but they're minus 36 and minus 16. I've had the advantage of being able to think about this before you've got here. So f at x equals 9x fourth, subtract 36x squared, subtract 16x squared to break apart that middle term into two parts. And now I can factor it by grouping. So my first two terms, I see a common factor of 9 and x squared. In the brackets, I will have x squared minus 4. I'm good. Okay. Second two terms. I know what I'm aiming for in my brackets is x squared minus 4, so I'm going to take out a factor of 16. X squared, let's hope this works. Subtract, yes, because negative times negative is positive, and 16 times 4, yes, is 64. So almost done. When I put this information together, I have the common bracket, x squared minus 4, and 9x squared minus 16. That's good, but it's not fully factored. Both of those brackets are difference of squares. So fully factored would be x plus 2, x minus 2 for the first one, and 3x plus 4, 3x minus 4 for the last. That's why we want your factoring skills all tickety-boo. So we have x-intercepts. I have an x-intercept from this bracket is minus 2. From this bracket is positive 2. From this bracket, well, that's not quite as easy. Let's go over to the side. 3x plus 4 equals 0. Going to solve for x, subtract 4, and divide by 3. So I have an x-intercept of minus 4/3, which is ugly. And this one, this x-intercept is very similar to the last one, but the sign is different, so it will be 4/3, 0. So I have 4 x-intercepts, which shouldn't surprise us because we have a quartic to the power of 4. We can have up to 4 x-intercepts. So I'm going to mark those on my graph, and then I need to know what happens at those x-intercepts. So minus 2 and 2. Minus 4/3 is minus 1 1/3, so it's in there, and positive 1 1/3. So this one's a little on the tight side. Each of those x-intercepts are to the power of, each factors to the power of 1, each one. So all of these are of odd order. So that means the function will pass through each point. I also know that I have a quartic, which is an even degree. Positive, because my leading coefficient is positive 9. So basically, I know the shape of this thing, similar to a quadratic, because I know a quadratic very well does that if it's positive. A quartic would be the same, but it might have some bumps in the middle. So I know what my end behavior is doing. What I know about these shapes is that as you go to the right, the function goes upwards, and as you go to the left, the function goes upwards. So putting that all together, and that my function passes through, let's write that blue. The function passes through each of these x-intercepts, and it's going upwards at the end. So I am just going to get myself started. I know it does that and that. I also know my y-intercept. That can help. At least it can get me anchored. My y-intercept is 64, which is, for sake of brevity, we're just going to put it up there, which is ridiculous. It's off of the scale. I know that my function will pass through and go down to negative and back through this x-intercept and up to positive, all the way up to the y-intercept. And then it's going to pass through this x-intercept below through that x-intercept and on its merry way upwards. So extremely approximately, that is my quartic. 9x to the 4 minus 52x squared plus 64. They also asked us to consider symmetry. Symmetry, unfortunately, uses the same words, but symmetry is where we are looking at odd and even. Now, when I have drawn my function, just from what I know of n behavior and x-intercepts, it looks like, well, it looks like a mess, but it looks like it is balanced, that the left side should be mirrored exactly on the right side. So they should look the same on the left and the right, or at least so it appears. If it is balanced across the y-axis, so symmetry across y-axis, we call that an even function. That's different than even degree. To check that something is even, we have this little thing we can use where if I substitute negative x into the function, I should get exactly the same as the function. So it's saying that the function on the left side is exactly equal to the function on the right side. So let's see if that is the case. If I put a negative x into my function, I'm going to scroll up for a second. 9x to the 4th minus 52x squared. 9, put in a negative x. It's amazing how fast I forget things. That's a minus and a plus 64. There. Let's tidy it up. 9. Negative x to the power of 4 is negative x times negative x times negative x times negative x, which is really positive x to the 4th. Take away 52 times. Negative x squared is really negative x times negative x, which is the same as x squared. I have substituted minus x in for x, and I have finished and gotten the very same thing as what I started with. That means this is, in fact, an even function, and it should look perfectly balanced across the y-line. It has symmetry in the y-axis. For the next example, we're going to find the equation of a polynomial function that has x-intercepts 2, 3, and 8, and it passes through a point 524. So if I have a polynomial function, call it f of x for lack of creativity, and I know it has x-intercepts 2, 3, and 8, then I know that once I have it factored, I'm going to have brackets that look like this. But it is possible that when I started my factoring business, there was a greatest common factor of some number. So I'm just going to call it a, my leading coefficient. So I know that my polynomial function, which has 3 x-intercepts, would look something like that. I realized as I was doing this, I gave you a missing piece of information. Specifically, these x-intercepts are all of order 1. Or I could have told you it was a cubic, but I was just, while I was thinking about it, I thought, oh, I didn't tell them if there's any bounces or passes through. These are all of order 1, so it is a cubic, and the function will pass through each one of these x-intercepts. Since we know that, the form that I've got it right there, and I know that it passes through a point 524, then what I need to do is substitute that point into the bare bones function that I have and solve for a. So 24 goes in place of y, or f at x. I have a that I'm trying to solve for, and every x will be a 5. So substituting, I get that. I just need to tidy up a little bit. This is 3, 2, negative 3. Negative 3 times 3 is negative 9 times 2 is negative 18. Divide both sides by negative 18. And I guess it would be good to simplify as much as possible. 6 goes into the top and the bottom. So a my leading coefficient is negative 4/3. So my function is negative 4/3, x minus 2, x minus 3, x minus 8. And why would we want to expand that? Let's just leave it the way it is. Let's draw a rough graph. We know that we have x-intercepts at 2, 3, and 8. 2, 3, and 8. 1, 2, 3, 4, 5, 6, 7, 8. There we go. I have a negative leading coefficient. And this is a cubic. So I know basically, just like a line, my cubic, when it's negative, is going to look like that. And it's going to pass through each one of those x-intercepts. So it's going to do that. It is going to pass through. I know that my graph is off scale because I do know that the point is 524. At least the only point that I've been given is 524. 1, 2, 3, 4, 5. So this right here is 524. My scale is a little wonky. 1, and so on. So that is a rough estimate of our graph from the x-intercepts and what we know about polynomial functions. Let's look at the last example. We have a table, and we are going to determine the equation, and I'm doing this just for Connor because he loves it so very much. First thing I want to determine is what type of polynomial function this is, and I'm going to look at first differences, second differences, and so on till I determine which of my choices I have. So first differences. I'm going to subtract. 0 take away negative 5 is 5. 5 take away 0 is 5. That's hopeful. 22 take away 5 is 17. Whoops. 63 take away 22 is 41. 140 take away 63 is 77. And 265 take away 140 is 125. Yes. Okay. So first differences are not the same. It's not a line. And you knew that would be too easy. Second differences. 5 take away 5 is 0. 17 take away 5 is 12. 41 take away 17 is 24. 77 take away 41 is 36. And 125 take away 77 is 48. Third differences. 12 take away 0 is 12. 24 take away 12 is 12. See a pattern? 12 and 12. So the most important part is determining that this thing is a cubic. And I know for cubics, I'm expecting my leading coefficient for your basic y equals x cubed to be, you have this somewhere on your cheat sheet, I hope, should be 6. For a quadratic, it's 2. For a cubic, it should be 6. This one is 12. So that means my leading coefficient is 2. So we knew a lot more than we thought we did. We have a function that I know has leading coefficient 2, and it is a cubic. Plus bx squared plus cx. I don't know those. And the last that I put into my equation is the y-intercept. I have the y-intercept. It is that. There we are. My equation looks like that. I need to know my b and my c. In order to find b and c, I'm going to need to substitute 2 points. So I'm going to choose the easiest ones. I'm going to choose 1, 5. And I am also going to use 2, 22. There's a reason that I need 2, and we'll show you that in a moment. Okay, so I'm going to substitute 1, 5 in here and see what happens. So my 5 goes in for f at x. 1 goes in for every x. And I'm going to have to tidy this up in a moment. Thank goodness that's a 0 on the end. All right, 5 equals 2 times 1 cubed is still 2. B times 1 squared is still B. And C times 1 is still C. One last line. I'm going to subtract 2 from both sides. 3 equals B plus C. That is one equation with 2 little letters of the alphabet. I'm going to use that in a moment. Second point I'm going to substitute is 222. So I put 22 in for y. I'm going to put a 2 in for x. Everywhere I see an x. There. I need to tidy that up quite a bit. 22 equals 2 times 2 cubed is 8. Always do your cube first. B times 2 squared is 4. And C times 2. 22 equals 2 times 8 is 16 plus 4b plus 2c. Couple seconds more here. Going to subtract 16 from both sides. I'm going to get 6 equals 4b and 2c. That's fine, and you can use that one. I'm just going to divide both sides by 2 just to make the numbers as small as possible. So 3 equals 2b plus c. I have 2 letters of the alphabet that I want to find a value for, b and c. And now I have 2 equations that will allow me to find their value. So here we go. I'm saying so a lot tonight. There we are. Equation number 1. We are going to solve for b and c. Equation number 1 for b and c is 3 equals b plus c. The other one that I got from a different point was 3 equals 2b plus c. There are so many different ways that you can solve this, but what I like to do, we call elimination, where I take my 2 equations and I can subtract them so that I don't have any c's left. And then I can solve for just b, because I can only do one thing at a time. So on the left side, if I do 3 take away 3, I will get 0. On the right side, if I do b subtract 2b, I get negative b. And c subtract c is gone. It's 0. Divide both sides by a negative, and my b is 0. Yay! So if my b is 0, and I put that 0 back right here, that means that c equals 3. And I got that from substituting, b equals 0 into equation 1. That's where I got that. So I have my b and my c value. Final answer, f at x equals 2x cubed. My b was 0, and my c was 3, and my y-intercept was 0. I am done. I have the equation of that function. Please be sure that your first focus as we get ready for a test coming up is to have a cheat sheet that you can use. You may want such information as this. What is the expected leading coefficient for a particular polynomial equation? You may want to have things about your graphing calculator on your cheat sheet. You should have the front side that talks about end behavior and what we expect. You may want a point on your cheat sheet about whether your x-intercept, if it passes through your x-intercept or bounces at your x-intercept, and so on. We'll talk about review in class tomorrow, but you'll want to get your cheat sheet all ready to go. For this stuff, page 108, 1 to 15, and some particularly good questions, 1 to 5, 10, and 11.